In this video, we're going to take a look at section 2.3 on graphing, more graphing like we did in 2.2, but this time we'll use a different technique called transformations. So graphing by transformations. In order for this method to work, so if you think about the word transform, that is the Greek word, I think it's Greek, for change. So we want to talk about how a graph changes. And the change we see in the graph will be based on the change we see in the equations. But in order for this method to work, we have to start with a baseline. We have to start with a baseline equation and its corresponding graph, and then look for changes to that baseline in the equation, and then make the corresponding changes to the baseline graph. So you have to memorize what the function's graph looks like depending on the type of equation you have. And so we have these families of functions, and it will be incumbent upon you to remember the basic equation. I call them basic equations because I don't know why I don't remember learning this material when I was younger. Or maybe I did, but the language changed for this material. But I noticed it somewhere else at some point that they call this the parent function. So I think that's the proper term for that. But you want to remember the basic equation, which is the simplest one you can have of that type, and its corresponding graph. You just have to know these in order for this method to help you. And this method is useful. It makes graphing easier to do because you'll already know the shape of the graph. You'll already know roughly where it's located, and you'll know some other changes that might happen to it. And then it's just a matter of plotting a couple points just for accuracy's sake. But you'll basically have an idea of what the graph looks like using this method before you even start drawing it. All right, so we have the absolute value family. So f of x equals the absolute value of x is the most basic absolute value function that you can have. That's the one you want to memorize. And the corresponding graph to that is the V-shaped graph. And an important feature of the V-shaped graph is that, and it's kind of hard to tell on this. Now, I'm not trying to brag or anything, but it's sort of a hobby of mine, like HTML coding. I just like to, write JavaScript code, HTML code. And so there was a time where I worked on a graphing tool using HTML, and I don't remember the software that actually did the drawing. I don't think it was HTML5 because I don't think that was available at the time, even though I think that would work now. HTML5's come a long way. It can draw things on canvases. But this software that I was using to do this graph had a little glitch right here. So you can see that the pointy end of the V should be directly on the origin, but it's a little bit above it where it shouldn't be. And that's just maybe not a glitch in the software even, but maybe a glitch in my programming, the code that I wrote for drawing these graphs. So the pointy end of the V should be at 0, 0. All right. Okay, and it's a V shape. It's a straight line going this way, straight line going this way. Notice we have the point 1, 1, 2, 2. That's the basic graph for the basic function. Now, for the problem we're actually given in the homework, it won't be the basic one. And so we'll start with this graph and we'll make some changes to it based on what's different in the equation that we're given. And so we'll have to learn that when this change is made to the equation, I will make this corresponding change to the graph. That's the strategy with graphing by transformations. Now underneath, I don't know why I include this information. It's in the textbook as well. For the parent function, for the basic function, these are the characteristics of it. But many of these characteristics, I'm having trouble talking, will change once you make changes to the graph. So for example, the range for the basic equation, for the basic graph, is 0 to infinity. But if I shift the graph down by 4, then the range becomes -4 to infinity. So I don't think it's really worth memorizing these characteristics that are down here. In fact, I'm not even going to scroll up for you to see them because I don't think it's a good use of your time to remember these. You want to remember the equation, the way the equation looks, and what the graph looks like. And for the way I apply the method, you definitely want to know this one point, 0, 0, in the basic graph. And you'll use that to help you figure out where the V-shape moves to once we get into these problems. All right. So there's absolute value as a family that you need to know. There's the square root family of functions, the most basic member of which would be f of x equals the square root of x. So that's as basic of an equation as you can have and still have it be a square root function. And so this is the one you want to memorize. And its corresponding graph is this shape right here. It's actually a parabolic shape. It's sideways, and it's just the upper half of the parabola. The bottom half is not there. So when I try to describe this verbally, it sounds confusing, but it's half of a sideways parabola. That's the best way I can think to describe a square root function's graph. Right. Now for the basic square root function, I want to point this out on this one as well. It also has the point 0, 0. That's in fact where the graph begins for the basic square root function. All right, so you want to memorize that equation and that graph that you see on the screen right now. You need to memorize it in order for this method to work. And then the last family that I'm going to ask you to remember. So maybe I should do more than this, but I really focus my attention on these three families of functions. There are other ones, not only that just exist, but that are also referenced in the textbook and there are homework problems on, but I just limit it to these three, for better or worse. All right, this is the square function. It's also known as a quadratic function, and we will actually dig deeper into these square functions, these quadratic functions, in Chapter 3. But for now, we're just going to learn how to graph these using transformations. And so it is a parabola where the bottom of that parabola, known as the vertex, we'll get into that in Chapter 3 as well, but for now we don't really identify it. Right, is that 0, 0? Oh, I'm still drawing that 0 horribly. Okay, let's try one more time. Okay, there we go. And it's a parabola. Okay, and so you want to remember that equation, what it looks like, the basic square function, and its corresponding graph. Have those memorized. All right. I might mention the other family of functions. I can't remember if I have them on the following screens, just to make you aware of them. But for the homework, I really just focus on the three I talked about. Yeah, it looks like I don't have any more. And this is kind of a weird thing. Now, this S should be over here, transformations. So the other families, I guess I decided to cut out of this presentation, but the other ones would be like a cube function, x to the third power would be the basic one, cube root function, and the linear family of functions, which I really don't like to include here because we already have strong methods for graphing lines. We don't need to learn another method for graphing linear equations. Slope and y-intercept or x and y-intercept are really efficient ways of graphing those equations. Very accurate, very efficient. There's no way to improve on that, so I'm not going to include those here either. All right, so anyways, I obviously just left those out of the presentation, but I just wanted to mention them. And I don't think you'll see any of those on the homework. So for transformations, what different kinds of transformations do you need to know for this course, for this section? So there are three basic types of transformations that you will be expected to know. One of them is reflections. Now, there are different kinds of reflections. I always tell my students, I usually do an example, right? So I'm just grabbing something that's nearby. Maybe I should use something else. So this is my phone. And so I can flip my phone over the x-axis. So if you think of the x-axis as the horizontal axis, I can flip it over that way, right? That's one way to reflect my phone, and that's one way to reflect a graph. But you could also flip it over a vertical axis. So if you think of a vertical line going through the middle of my phone, I can flip my phone over this way, right? And that'd be another type of reflection. So I can flip it that way or I can flip it that way. Those are the two main types of reflections that you would commonly see with this material. But you can flip over graphs in other ways. So another one I like to do is like diagonally. So grabbing the phone by the corners here, and I could flip the phone over about a diagonal line, right, like this. And so that would be another type of reflection. This course, because I've taught out of different textbooks previously, and a lot of them will do reflections about the x and y axis, and they can get kind of confusing figuring out which one's which and how to apply it. This textbook really only has reflections about the x-axis, so we only have to worry about that one for this particular course. So again, if you're one of my students, that's all you got to worry about, reflections about the x-axis. If you happen to be watching this video because you stumbled upon it on YouTube, you'll have to check with your course, your teacher, to see if you need to do further research on reflections about the y-axis, because I will not be covering that. Another type of transformation would be translations. And there are two kinds of translations. A translation literally just means moving the graph from one spot to another. So reflection is flipping it over. So, I like to use the analogy of, like, on your computer, you can take an image and you can flip the image over. That's often something that you can do with images on a PC or a Mac. You can also move the image. So imagine that you're, like, typing up something on Microsoft Word. Well, you can take the image on Microsoft Word and flip it over. That's a reflection. Or flip it over this way if we're going about the x-axis. You can move the image to a different spot in the document. That's a translation. That's what we call translations in mathematics. And while we can move it, like, we might say, okay, here's where my picture's located, and I move it diagonally like this. So if it's on Microsoft Word, I might just drag it in a diagonal direction. In math, for this material, we're going to break that down to vertical change and horizontal change. So we're going to look at vertical translations, moving the graph up or down, and horizontal translations, moving it left or right. And taking those in combination will cause the graph to move in a diagonal direction, right? If I go up and to the right, which I know on my screen might be looking like I'm going to the left, but it's my right. So up and to the right, that looks like I moved the graph diagonally, right? But I'm breaking it down into vertical and horizontal components. The last type of transformation that you'll need to know is stretching or shrinking. And this is on a computer resizing the image, right? So imagine again, you're on Microsoft Word and the image is too big, you want to shrink it down, or maybe it's too small and you want to expand it, right? That's stretching or shrinking. That's what we're going to call stretching or shrinking. It's the same idea. The picture still looks the same, right? The image is still the same image, but it's either smaller or bigger, right? So for math, it'll still be a parabola, right? So when you stretch or shrink a graph, the shape stays the same. It's still a parabola shape, or it's still a V shape, or whatever the graph is, but it's either more, like, what happens is when you shrink it down, or we're actually going to be doing stretching or shrinking just in the vertical direction. So on Microsoft Word, you stretch or shrink in proportion. Usually you grab the corner, and that way it shrinks both horizontally and vertically at the same time, so that the graph maintains the proper ratio, or not the graph, but the picture maintains a proper ratio so it doesn't distort it, right? But in math, we're not going to be doing that. We're just going to be stretching or shrinking the graph only in the vertical direction, so it will be distorted. So we'll be taking, like, a parabola shape like this, and if we shrink it vertically, it'll flatten out. It'll be more broad. If we stretch it vertically, it'll look more narrow. And so it's gonna distort the image, but the shape will still be the same shape. It'll still be a parabola. It'll just be like a distorted parabola. It'll either be flattened or stretched out. Right. Okay, so what we need to do is learn how to recognize when these transformations are occurring by identifying changes that are being made to the equation. So we're going to look for changes in the equation that signify reflections, translations, or stretching or shrinking. And once we've identified those signals in our equation, we will apply the corresponding change to the graph. We'll either flip the graph over, or we will move the graph, or we will stretch it or shrink it if we see that signal in the equation, right? So instead of going through it one at a time, because we could talk about just reflection, just translating horizontally, just translating vertically, which is what the textbook does. I find it's easier just to kind of throw them all together. I'm pretty sure that's what I'm doing here. I should have looked at my presentation ahead of time. It's June right now. The last time I taught this material was back in like February or March. So it's been a while since I've done it. So I apologize if it looks like I don't know what I'm doing. So this is sort of like the worst case scenario of having every type of transformation lumped together into one equation. Now, we're using function notation here, so I'm not being specific about what the actual family of function, the function family is that we're going to be using. So this example is not specific about, is it an absolute value, is it a square root? It applies to all of those. It applies to any kind of function, right? So this could easily be absolute value of x minus h. This could be square root of x minus h, right? The function, you know, how do I want to say this? It's one of those functions, right? But we're not specifying that because that's not what we're trying to focus on right now. So what are the different changes that are being made? So the original function is just f of x. Everything else that's added to this new equation y is a change that's being made to the equation. And each of those changes is going to have an impact on what the graph looks like. Every change in the equation is going to cause a change in the graph of that particular function, right? So I don't know which one to start with here. The negative sign indicates that there will be a reflection about the x-axis. So if you take, it's kind of weird. If you take your original function and put a negative sign in front of it, that's going to flip the graph over the x-axis. That's how you'll recognize when that change needs to be applied. You'll have a negative sign in front of your function. So if it's absolute value, you'll have a negative sign in front of the absolute value. If it's square root, you'll have a negative sign in front of the square root. And that's how you'll know there's a reflection occurring. All right. The minus h that you see inside of the parentheses, this is happening inside the function, which is why when I wrote these examples here, I put the minus h with the x inside the absolute value or inside the square root. This is going to be a translation. And an easier way to say translation instead of writing out all those letters, in that word, you could just say it shifts the graph. Shift would be another way of saying translate. So this will shift the graph horizontally. By h units. So that's how far you want to shift it. So if there's a 1 here, you want to shift the graph 1 horizontally. If there's a 2 there, you want to shift it by 2. Now you have to decide which horizontal direction do you want to shift it. Do you want to shift it to the left by 2, or do you want to shift it to the right by 2? So you shift it to the right when h is positive. Instead of writing out that h is positive, in math we have a much easier way of indicating when something is positive. We just say greater than or equal to 0. Or not equal to, excuse me. I don't know why I threw equal to in there. I said equal to, but on the screen I just wrote without the equal to, because if it's equal to 0, it's not positive. And if it's equal to 0, it's not happening, right? If h is 0, there is no horizontal shift. And so you can't really have h equal to 0 if a shift is occurring. So it's to the right when h is positive, and this is how we say positive in math, greater than 0, not equal to. Sorry about that gaffe. And you're going to shift it to the left when h is negative, and the way we say negative in math is to say less than 0. Right. Now, if h is positive, so let's say h is equal to positive 1, and I plug that into this formula here, and I'm plugging in 1 for h, what is that going to look like? That will give me x minus 1 inside the function. And so then I'll get something that looks like this. I'll get absolute value of x minus 1, or square root of x minus 1. And this is the case where h is positive. H is equal to 1 in this case, which means it shifts it to the right. So it's going to be a little confusing because in the equation, you'll have a minus sign in front of that number. But when there's a minus sign there, that's the case where h is a positive value. And minus 1 is the case where you want to shift the graph to the right one. And that will throw students off because your intuition is going to tell you, oh, minus 1, I should shift it to the left because it's negative. And negative, to the left is the negative direction. but it's opposite. It's kind of backwards, if you will, for horizontal shifting. So if it's a -1 directly on the x variable, that actually will shift the graph to the right one. And if maybe I'll do an example to illustrate why that happens, because you might still feel like that doesn't seem right to me, but there's a reason why it behaves that way, and I can show you an example to illustrate that. If h is negative, right? So let's say h is -2, for example, and I plug -2 in here for h. What is that going to look like? I'm going to get x minus -2, which is going to give me x plus 2. So if I see absolute value of x plus 2 or square root of x plus 2 as my equation, having a plus sign in front of that number tells me that that's the case where h is negative. And that's going to shift the graph to the left too. All right, so if you see a plus sign with the number, it'll shift the graph to the left. If you see a minus sign with the number, it shifts it to the right. And it has to be adding or subtracting directly to the x variable inside the absolute value or inside the square root or inside the power of 2. I haven't really used that as an example, but that would be another case of where you would shift it to the left or right. It has to be added or subtracted directly to the x variable. All right, so that's how you will recognize when there is a horizontal shift in the graph. The plus k indicates, let me pick a different color here, a vertical shift. So we will shift vertically, in this case, by k units, whatever that number happens to be. And it works the same way as horizontal shift. Let me pick a different color here. It'll be up when k is positive. And I really don't like the way I write zeros on here. It really bugs me. I can't seem to join back to where I start very well. Okay. And it'll shift down when k is negative, which means less than 0. All right. Now this one, notice there's a plus sign in front of the k. So when k is positive, like let's say k is equal to 3. That's positive 3. If I plug 3 into this formula for k, I'll get plus 3. So this one, it behaves differently than this one does, right? So for horizontal, the graph actually shifts in a direction sort of opposite of the sign that you see in the equation. But for vertical, it goes in the direction of the sign that you see in the equation. So if you have plus 3 in your equation, so for example, if I have absolute value of x plus 2 plus 3, the plus 3, which is outside the absolute value, it's not added directly to x, it's just tacked on to the end of the function. That's where the plus k is, right? It's not inside the function, it's tacked on to the end of the function. That's going to shift the graph up 3 because this is a case where k is positive 3. So plus 3 actually does shift the graph up 3 like your intuition would expect. And if k is negative, like if k is -4, for example, we would have -4 here, plus -4 would make it a -4, right? And that would actually shift it down 4. Because here is the case where k is negative, negative is going to shift it down. All right, so we've talked about reflection, how to recognize when that's occurring. That's an easy one if there's a negative sign in front of the function. We've talked about horizontal and vertical shifting. Those are a little bit more difficult to decode. The last one, the one we haven't talked about yet, and I'm running out of colors to use to make it easier to read, is stretching or shrinking, and that's where A comes into play. So if there is a number being multiplied to your function, if you have a 5 in front of the absolute value, or a 6 in front of the square root, maybe instead of using 6, let's do something a little different. If you have a 1/2 in front of the square root, right? That will be stretching or shrinking. If it's -5, that is both. It's stretching or shrinking and reflecting and flipping over, right? So the number determines whether they're stretching or shrinking. The negative sign determines whether it's being flipped over first or not, right? So this would tell me that there is stretching occurring. It's stretching if that number A is bigger than 1. So 5, that's bigger than 1. The negative is not part of that. The negative means we're flipping the graph over. It's being reflected. right? The 5 is what tells me if they're stretching or shrinking. And it's a bigger than 1 number, so they're stretching in that case. If the number is between 0 and 1, that's shrinking. Now, I don't think you're really going to be tested on, I'm not going to say, oh, you called it stretching when it was actually shrinking. You lose a point. Nobody really cares about that. So if you call it stretching when it's really shrinking, I don't think most teachers are going to penalize you for that. Maybe I'm wrong. I wouldn't penalize you for that. But if it's between 0 and 1, it's shrinking. And again, if you're thinking, okay, well, bigger than 1 stretching, 0 to 1 is shrinking. What about if it's negative? Again, the negative sign doesn't have any impact on the stretching or shrinking. If you have a negative number there, the negative sign is dealt with separately as a reflection. It is flipping the graph over, and you divide that, you divorce that from the number itself for the stretching and shrinking, right? Okay, and so that's stretching or shrinking. That's how you'll recognize that. So I'm sorry, this is a big mess, but it just takes forever to go through these one by one. And I have found I really lose students' interest when I do that. So I have found it's more effective, it's more efficient, and I keep people's attention better if I just say, let's just talk about all these together. And now you can kind of see the way you will decode your equations. You can see them all together in action, how you'll know where you get each piece of information from. So let's try to see if we've picked it up well enough by looking at an example. So the first thing you want to do before you start identifying the changes to make, you have to know what you're starting with first. What kind of graph do you want to start with? Is it a V shape? Is it a parabola? Is it a square root function, a sideways parabola, right? So the first thing is to identify the family of the function that you're currently working with. This is clearly an absolute value function, right? This is absolute value, and that graph is a V shape. So that's the first thing you want to decide is what family of function am I currently working with in this problem. Once you've identified the family that you're working with, you want to start with the most basic member of that family. And that's what I asked you to memorize earlier in the video. And so the most basic absolute value function is just absolute value of x. I've memorized that equation. And I've memorized the graph for that equation. It's a V shape where the pointy end of the V is at 0, 0. All right, so I'm trying to bubble that in there. And that's all the detail I bother to remember. This is just it's a really rough sketch of that basic absolute value function. Some approaches, some textbooks will tell you to remember more than just this. They'll say, memorize these points. I pointed them out earlier, 1, 1, 2, 2. I don't think you really need that much detail yet. Now, the final product, the graph that we get over here, we want that to be accurate. We want it to have some details to it, but I don't think your beginning product needs to have that much detail to get the right answer. So because again, I'm looking for simple. I have a bad memory, honestly. As you can tell, I couldn't remember my own lesson. I couldn't remember what do I have next after this. My memory is not the best. And so I want to minimize the amount of things I need to remember. And so if you want to minimize that, this is all you need to know. This is what the equation looks like. It's a V shape, pointy end at 0, 0 to start. Now what I do is I compare this basic absolute value function with the function I'm given in the problem that I'm trying to find the graph of, right? So I have this one memorized. I've memorized the graph for this function, but I'm looking for the graph of this one. And what I want to do is find the differences. So you remember from, Highlights magazine, right? You have two pictures side by side that look really similar. And the game was to spot the differences. Look for what's different in the two pictures. That's what you're doing here. What's different between these two equations? Each difference that you can identify in the equations will cause a certain change to occur in the graph. That's the game we're playing right now, right? So what's different between these two equations? Well, I see a -2 inside the absolute value directly on the x variable, and I see a +3 tacked on to the end of the function. That's it. If you take those two numbers away, this equation looks exactly like this, right? So these are the only two things that are different in this equation that are missing from over here. Each of these two differences is going to cause some kind of change to this graph. And I always start with the one inside the absolute value, the number that's being added or subtracted directly to x. Start with that one first. That's a -2. That's going to shift the graph to the right 2. So remember, for left and right, it's backwards of that sign. -2 makes me think that the graph would go to the left because negative is to the left, but it actually bumps the graph to the right. And like I said, I'll try to find a good moment to discuss why that happens, but not right now. Let's go ahead and finish this problem first. So I want to take my basic graph and shift every point on this graph to the right 2. But what I do is I call this my tracking point. I'm just going to track where this point goes first. And then I'll worry about the rest of the points later. So this point, every point on the graph is getting shifted to the left 2, but I'm going to track this one first. This point will get shifted to the left 2. And then the +3, that's tacked on to the end of the function. That's not directly on the x variable. That's going to shift the graph up 3, right? So that's going to be a vertical change, a vertical shift. +3 actually does shift the graph up 3. And so all the points are going to get shifted up 3, but I'm just tracking this one for right now. It's going to get shifted to the right 2, and then it's going to get shifted up 3. So where is it going to end up? So it's going to end up, and I'm going to actually mark it over here where my final answer is going to go. I'm starting here at 0, 0. I'm shifting that point to the right 2 and then up 3. Let me see if I can make sure I'm marking this in the right spot. All right, so it's going to be right there. So the point that was at 0, 0 is now going to be found at 2, 3. I almost said -3 for some reason. It's going to be found at 2, 3. Now, if this was a perfectly drawn graph, if I took the time to mark these points so this graph was exactly right, all I would have to do is copy the V shape and paste it here. It's just, shifting. If that's all that's happening to the graph, it's simply a copy and paste job. You're copying it from its original location and pasting it to its new location. That's all that's happening with the V shape. But this is not a perfectly drawn graph. And even if it was, on paper, I can't copy and paste. We're going to have to redraw it over here in a precise manner. So what I always recommend doing is once you know, so think about what we know so far. I haven't really completely drawn it in, but I know that this graph is a V shape, and I know it's located right here, right? I know that the pointy end of the V, I know this for a fact, starts at 2, 3. That's where the pointy end of the V is. And then from there, we have a V shape. So we have a really good idea of what this graph looks like. We know where it's located, we know the shape of it, but it's not quite as precise as we would like it. And for Math Excel, you're going to have to plot at least one more point so it knows exactly how to draw that V shape. So I'm going to undo that drawing because that's really a good idea of what the graph looks like, but I just want to make it as precise as possible. And the way we're going to do that is by plotting a couple of points. Right. But it's not like 2.2 where we're having to plot points at random by just picking random values for x and plugging them into the equation and getting answers for y. We're going to choose these more carefully because we have information at our disposal, right? We know where this V shape is located. We already know one point. It's at 2, 3, so I don't need to choose 2 for x. I already have that point. But I need to have at least one point to the right of that in order to make this V shape look as accurate as possible. It's a straight line. I just need one more point to draw that straight line to the right. So I'll pick 3, right? That'd be the next best choice to make there. So I'm not wasting my time choosing 0, 1, and 2 because 0, 1, and 2 are just going to give me half of the V shape. I need another point on the other side to know what the other half of the V shape looks like. But I know all of this because of transformations, because I memorized the shape of the graph to begin with, and I know where it's roughly located right now. And using that information, I can more surgically choose the points that I want to graph, right? To get precisely the information I need. So I'm being more efficient in my choices here. I'm not just randomly picking -2, -1, 0, 1, and 2 for x, which is what a lot of students do. That's not going to actually help you out here, right? You want 3 for x. So I'm going to plug in 3 to this, not to my basic one, but to the one I'm trying to graph, right? So y equals absolute value of 3 minus 2 plus 3. This is going to be the absolute value of 1 plus 3, which is going to be 1 plus 3, which is going to be 4. Right. And so I have the point 3, comma 4. I feel like I really can't see these lines very well. I probably should go get my glasses. And from there, I know it's a straight line. So let me use the straight line drawing tool. It's going to go like that. Right. So that's the right half of the V shape, but I want to make sure I do the same amount of work to get the left half correct. Now you could choose another value for x over here on the left-hand side. So you could choose 1, for example, or 0 would be a good choice. Whoops, didn't realize I was still on the straight line drawing tool. 0. Or you could use the fact, and this is getting a little bit ahead, this is a little bit of advanced subject material, but I don't know if that makes sense what I just said. It's kind of redundant. So this is a little bit of advanced material, but the V shape is symmetric, meaning the right half of the V is just a mirror image copy of the left half of the V shape. And so for every point that you get on one side of the V shape, there is a mirror image point the same distance away on the exact opposite side of where the V turns. Now for the basic function, it turns on the y-axis. So the symmetry is about the y-axis, but we've moved it, right? So now the symmetry is about the line where x is equal to 2, right? This is where x is equal to 2. That's where the symmetry is now for this V shape. So for every point on this side, on the right side of this vertical line, there's a mirror image point the same distance away on the other side. So this is 1 to the right of this vertical line. That means there's a mirror image point 1 to the left, which would be right here. And so I can use the symmetry to determine another point on the other side, and then from that I can draw a straight line. But if you don't like using the symmetry, you don't need to do that at this point. You can just pick another value for x. So I could pick x equals 1, plug it into the equation. We get 1 minus 2, which is going to be -1. The absolute value of -1 is +1. 1 plus 3 is going to give me 4, and I would get 4 again. Right? So 1 comma 4, which gives me that point. And then we will draw a straight line connecting these two. All right, and there's our graph. And it's, what's nice about this method is it's accurate, it's efficient, it's precise, so we get our graph quickly and accurately. That's what we're going for here. All right, now it also asks for domain and range. So after all that work, we still have to do one more thing. I'm sorry, that kind of looks like it added itself to the equal sign, but domain and range. So the domain, remember, how far to the left does the graph go? How far to the right? In this case, the graph is going to go forever to the left, forever to the right. So the domain is -infinity to infinity. The range is how far down the graph goes, how far up it goes. So in this case, how far down is the graph going to go? It only goes as low as 3. That's the lowest y value on this graph. It gets as low as 3, right? This is the lowest point right here, and that y coordinate is 3. How far up does it go? It goes up forever. So the range is going to be 3 to infinity. So that's the domain and range. All right, let's take a look at the next example. All right, so this one's multiple choice. I would say this is probably, I don't know why I'm having such trouble remembering. This just seems so different to me. I think I know why now, because I think I made this presentation fairly recently relative to the other presentations that I have for my other sections, because for this section we were trying we're doing something kind of experimental with having students watch videos before coming to class, and so we had a whole different thing, and we kind of abandoned that, and so then I just made this lesson to replace it. And I think that's why it seems so new to me, because I really feel like I don't remember doing this too often, so I might have only used this once or twice in the past. Anyways, I think you guys should try this one, because it's really not too different than the problem we just did. So pause the video, make your choice. Which of these graphs appears to correspond to the changes that need to be applied based on what you see in that equation, and then resume the video to see if you came up with the right answer. Okay, so the correct answer here is graph A, and you can determine that to be the correct answer without really having to do too much work. You just look at the equation you're given. This is part of the square family, so we're comparing this to f of x equals x squared. What's different? Well, we have a plus 5 here, we have a plus 4 here. The plus 5 will cause the graph to shift to the left by 5. Again, it's a plus, but it's going to actually cause the graph to go to the left. And the plus 4 here, on the outside of the function that's tacked onto the end of the function, will shift the graph up 4. And so looking at our options here, only one graph comes close to mimicking those changes. Mimicking maybe is not the right word, but whatever, which is graph A, right? Graph B shifts to the left 5, but does not shift the graph up 4. It's just only has shift to the left 5, and that's it. Graph D maybe is the one that's the most commonly chosen incorrect answer, because this is shifting the graph to the right 5 and up 4, and that is a common mistake students will make. When they see the plus 5, they'll think the graph should be shifted to the right instead of the left, and so that's not correct. And C, nothing. They didn't make any changes at all, right? They just left this as a parabola at 0, 0. No transformations were applied to C, and so that could not be correct here either. Now let me take a moment, because I keep talking about it. Let me go ahead and explain why plus 5 will shift the graph to the left 5. So to do that, you have to think about the basic function, right? And the points that work on this basic function. So we have 0, 0. If you plug in 1 for x, you get 1 squared, which is 1 for y. If you plug in negative 1 for x, you get negative 1 squared, which gives you positive 1. And then if you plug in 2, you get 2 squared, which is 4 for y. And then negative 2 also gives you positive 4. That's for the basic function, right? And it's going to look something like this, right? It's going to be 0, 0, 1, 1, 2, and then 4, right? You get the idea. Now, if I take, I don't know if I want to use 5 here. Let's use a different number. So if I have y equals parentheses x minus 2 squared. That's a minus 2 here. So if I, find some more solutions to plot as points for this one, if I want to maintain the same y values, so I want to stay at 0 for y on the first choice, 1s for the next 2 choices, 4s for the next 2 choices, how do I have to adjust my choice for x? So if I want to have the y coordinate be 0 here, what do I have to choose for x to make sure I stay at 0? Well, I would have to choose positive 2, right? So 2 minus 2. So by choosing positive 2, we get 2 minus 2, which is 0 squared, which gives me 0. Right? Whoops, I put the wrong number there. So I have to choose positive 2 in order to stay at 0 for the y coordinate. Right? So originally, I choose 0 for x to stay at 0 for y. But with the minus 2 here, I have to make a choice of x being positive 2 in order to stay at 0 for y, which is 2 more than the original choice for x. 2 to the right, right? Positive 2, which is 2 to the right of what originally worked to give me 0 for y. If I want to stay at 1 for y, what would I have to choose for x? Well, there's 2 things that would work. But one thing that would work would be 3, right? Because 3 minus 2, so if I plug in 3 for x, 3 minus 2 gives me 1. 1 squared gives me 1. And so I get 1 for y by choosing 3 for x, which is 2 to the right of the original number that would have given me 1 for y. I hope I'm saying the right thing there. I feel like I said the wrong thing a minute ago. All right, so if I want to stay at 1 for y, I have to choose a number for x that is 2 to the right of the original number that gave me 1 for y to get this particular one. Now we can get 1 another way, and that would be by choosing positive 1 here for x. Right? So if I plug in 1 here, I get I get 1 minus 2 squared, which is going to be negative 1 squared, which also comes out positive 1. So 1 would also work, but this one is 2 to the right of this original choice. Right? So in both of these cases, we're choosing x values here that are 2 bigger than what they originally were in order to stay at the same y value. So I have a couple more examples here because I thought maybe I'd need to also look at these, but I think that makes the point pretty clearly. So the reason why it shifts the graph to the right 2 is this minus 2 here forces you to choose x coordinates that are 2 bigger than they originally were in order to keep the same y coordinate. Right? So the minus 2 means x has to be 2 more than what it originally was in order to keep the same y coordinates. And that's why the graph ends up being shifted to the right 2, because it forces us to choose x coordinates that are 2 units bigger. All right, so I know I said that 3 times in a row, but I just want to make sure. I regret choosing the number 2 because now that kind of sounds confusing now, like TOO, but I mean TWO, right? Okay, so now, why doesn't that work the same way for the vertical shift? It actually does, but the plus 4 here was separated from the y coordinate. So notice the 5, or here the minus 2, is directly on the x variable. And it works in this way. Minus 2 shifts the graph to the right 2. Right? And I guess I didn't finish drawing these over here, but now we have 2, 0, 3, 1, negative 1, 1. These are all shifted to the right 2. And that's why the whole graph gets shifted to the right 2. That minus 2 is directly on the x variable, and that's why it behaves in that way. Minus 2 shifts the graph to the left 2, plus 5 shifts the graph to the left 5. Did I say that right? I don't know. I keep forgetting the words I'm just using, so I'm going to repeat it one more time to make sure I said the right thing. Minus 2 shifts the graph to the right 2, plus 5 shifts the graph to the left 5. All right. Now, for the vertical shift, this plus 4 is not with the y variable that it's impacting. It got separated from it and put on the other side of the equal sign. But if we join them back together, it behaves the same way as the horizontal shifting does. Right? So if I take this plus 4 and subtract it back over to the other side, so it's with the y variable that it's affecting, it behaves in the same way. Minus 4 over here actually shifts the graph up 4. And a plus 4 here would shift the graph down 4. But you never see functions written in this way. So this number is always separated from its variable, and that changes its behavior on the signs from what's happening with the horizontal shift. So that's why there's a difference between these two, in case you were wondering. So if you weren't wondering and you understood it before I said all that stuff, ignore what I just said. Go back to wherever you were when it was making sense to you and just stick with that. Because I don't want to, confuse you or make it more difficult, for you to figure out the right answer going forward. So, all right. Got a few more examples, and I'm sorry about how long that took to do. So here's another one. Now this time we have a negative sign here. So first of all, before we get into that, what's the family here? This is the square root family. And family is really easy to identify. I mean, it's the structure of the equation pretty much gives it away right away. This is a square root function. The most basic member of that family is f of x equals square root of x. So you're supposed to memorize that. And you're supposed to also memorize the graph that goes with that particular equation. So I've memorized the graph for this, and that's a really horrible drawing of that. So it's going to do something like that. All right. So again, this is not a great drawing either, but it has the right main characteristics. It's half a sideways parabola, and it starts at 0, 0. That's all you really need to start with in order to construct a good graph of the equation that you were given. Right. So the minus sign, as I was starting off saying, is going to flip the graph over, which is just a more informal way of saying reflection. And really we should be more specific, because remember in my example with my phone, I could flip the graph over this way, I could flip it over this way. I should be more specific about how I'm flipping the graph over, except that, as I mentioned in this course, we are only studying one type of reflection anyways, so I really don't need to be more specific than that because of our limited scope. Now, if we were going to look at other types of reflections, then I need to be specific here and say, we're flipping the graph over the x-axis, not the y-axis, not some other axis. We're flipping it over the x-axis. But for this particular textbook, that's the only kind that we are looking at anyways. So if you just say flip, I'll know what you mean, and that's fine. All right, so we're going to flip the graph over the x-axis. So here is the x-axis. We need to flip this graph over the x-axis, which we'll do in just a second. Plus 5, we already saw that example. This is going to shift the graph to the left 5. Minus 3, we'll shift it down 3. Now, when you start having multiple transformations in the same problem, you do actually have to be careful the order that you apply them in. And in the textbook, they kind of do this fairly complex ordering of the transformations, which is not the way I learned it originally, because I can't even remember how I learned this material originally, but it's not the way I re-taught myself to do it either, because again, I like to keep things simple. And so this is the way I suggest doing it, based on what I like to remember from the basic graphs, and the way I like to, based on the process that I use. This works. But if you want to use the textbook's process, again, they suggest memorizing more points than just this one. And then they track all the points through all the transformations. And then at the end, you don't have to plot points because you have all the points already and you know exactly where they all went. So that's one benefit from doing it the way the textbook explains it. But then if you do it that way, you have to actually kind of be careful the order you apply these transformations in, a little more careful than what I'm going to suggest, which is what I mentioned at the beginning, not the beginning, but here on this screen. So not only was this outlining the different types of transformations we need to talk about, this is the order that you should apply them in if you're going to use my technique. So we will do the reflection first. Now, if you're doing reflections with the y-axis, that might change the order that you should be applying these in. But with only the x-axis one, we can just do that one first. If there is one, if there is a reflection, do that first. Then do the translations. And what I like about my approach is that you can just do these together at the same time. So vertical and horizontal can be done simultaneously. And then we'll do the stretching or shrinking last, of which we don't have any in this particular example. So we'll flip it over first. And when I say, we do that first, we do that separate. So don't try to do all of these at the same time. Let's just do the reflection first. So we're going to, I guess, let me number these 1, and then we'll do these 2 together for step 2. So the way I think of this is I imagine picking this graph up by the x-axis, rotating it 180 degrees, and putting it back down. What would it look like if I did that? Well, the point at 0, 0 would still be at 0, 0, because when I pick it up by the x-axis and flip it over and put it back down, any points on the x-axis are going to stay right where they were. But this part that's above the x-axis, when I flip it over, is going to go below the x-axis. So it's going to look something like, really doing a bad job of drawing these. Something like this, right? So now the graph looks something like that. Again, it's a rough sketch. If this was going to be my final answer, this would not be acceptable. But we're working towards that final answer. I'll get it more precise at the end when I plot a couple of points. But this gives you a rough idea of what it looks like. It still starts at 0, 0, but now it's the bottom half of the parabola rather than the top half. All right. Then I will do the translations. I'll move the graph, copy and paste, right? And so let's draw that again. We're going to shift this graph to the left 5. So this point, and this is my tracking point, right? We're going to shift the tracking point to the left 5 and then down 3. All the points on the graph are getting shifted in this way, but I'm just going to track this one for right now. So where does this point end up going? It ends up going to -5 on the x-axis, and then and I probably should number these. Well, I'm gonna redraw my graph in just a second, and then we'll do -3 on the y-axis. Right? It's going to end up down here. Otherwise, the rest of the graph, the shape just gets copy and pasted to that new location. So it's going to look still exactly the same. It's just going to be located over here now. So it's going to look something like that. And that gives you a pretty good, even if we, weren't going to do anything else to make this graph any better, that's still a pretty good idea of what the graph looks like. It's the right shape. It's in the right place. You can find domain and range from that, right? It's detailed enough to do domain and range. So it gives you a pretty good sense of what the graph looks like. But I'm not happy enough with this because we want to get some points here. So I'm going to plot a couple of points. right? But again, I kind of have an idea of where I need to plot some points at, right? I'm going to go over here where, I know this point right here already, but maybe, right before it. So like -4 would be a good choice, for example. So I'll choose -4 for x, plug it in to the equation. So y equals negative square root -4 plus 5. I can't remember what was there. I was going to put minus. Is it -3? It is -3. Okay. Okay. And so we get y equals negative square root of 1 minus 3. That's going to be -1 minus 3, which is going to be -4. So we get -4 comma -4. So there we go here. Now this is going to be, it's probably still not going to be drawn as well as I would like, but this is going to be my final answer. So I'm going to make sure to mark these numbers carefully. We have -5 here. We have -3 here. We're going to have to go at least to -4. So we have -5 comma -3. We have -4. Sorry. I don't know why it draws my 4s like that sometimes. -4 comma -4. Now again, with 2 points, you have to be careful not to accidentally think, oh, that's a straight line. I'd say let's find one more point. Now we have to be careful with this square root, to get nice numbers to graph anyways. So if I choose -3, if that was your thinking that maybe that'd be the next best number to choose, that actually does not work out very well, right? If I put -3 here, -3 plus 5 is 2. Square root of 2 does not really simplify. What I would like to have here is 4, right? Because square root of 4 does simplify nicely. So how do I get this to come out equal to 4? I choose -1. So I'm not going to choose -3. I'll choose -1 instead. When I plug -1 here for x, I get -1 plus 5, which will be 4. The square root of 4 is going to be 2. -2 minus 3 is going to give me -5. Right. And so we'll get the point -1 comma -5. So let me make another mark here. -1 comma -5. And you can see that it levels out as it goes to the right. And so I'll try to connect these points. Oh, I kind of missed that last one. Try one more time. It's really hard to do on this tablet that I'm using. Okay, and so this is a good picture of the graph. All right. Now on Math Excel, it'll be multiple choice because there's no graphing tool to allow you to graph this manually. So I just left that off the screen because I wanted to show how you would figure out the graph without having that multiple choice to help you figure it out, because you saw how easy it was. This is the problem with multiple choice, right? I really don't have to know much about this topic to figure out which answer is correct here. And I could even know less than what I did by just maybe picking a point, right? I just maybe plug in a number for x, like 0 even, and that would pretty much give away which one of these is right. So just by plotting one point, I can figure out which choice here is correct without knowing anything about transformations or memorizing the shape of the graph or anything like that. So that's why I don't like multiple choice questions in math. So here we go. Now domain and range, right, is something else they will ask about, and that will not be multiple choice. So the domain, how far to the left, how far to the right. So again, we're doing this. How far to the left, how far to the right? It goes to -5, right? So how far to the left can I go? -5 on the x-axis. How far to the right? It goes forever to the right. So the domain is -infinity to infinity. What about the range? How far down? How far up? The graph goes down forever. Now it's mostly going to the right, but the pattern here is it's going to head to the right and down. And it does that forever. So it's going to go to -infinity for down. How far up does it go? Well, the highest point on the graph is right here, which reaches -3 on the y-axis. So it's going to be -infinity to -3. All right, so let's take a look at, I have a couple more examples here of transformations. I'm sorry the video already hit an hour, and we have one more topic after this one to talk about. So maybe I've done a little bit too much talking on this video, but I apologize. Again, you're in control when you're watching the video, so you can kind of, if you find I'm doing right now, going a little bit off topic, you can kind of skip ahead and try to find where I get back on topic. All right, maybe that'll shrink the run time of the video down for you to something a little more reasonable. Use transformations to graph the function, state the domain and range. So this one, it's really kind of repetitive. We just did a square root function and now we're doing another one. But what's different about this one, so I guess, this is going to start off the same. This is a square root function. Here's the basic square root equation. And the graph we've memorized for that is this right here. What is different about this one is that we have all the transformations happening at once in this problem. Right? And so we have a negative sign. So again, spot the differences, right? Just like Highlights magazine, right? Spot the differences. The negative sign, now we have a -2. Now a lot of students will put these together. They'll say, oh, there's a -2 here. And this is a really horrible example, isn't it? Because like they're all 2s. So when I say 2, you don't know which one I'm talking about. But we have 3 2s here that aren't present in the original basic equation. So all of these changes, all these differences are going to cause changes to the graph. And we want to identify what those changes are going to be. And a lot of students will lump the negative and the 2 here together, but they actually indicate 2 different changes that have to be made to the graph. So the negative sign in front of the function is going to flip the graph over. The 2 is stretching or shrinking. And if we want to be specific about it, this time it's stretching because it's bigger than 1. It's going to be stretching. The +2 is going to shift the graph to the left 2. And the -2 at the end is going to shift the graph down 2. So I need to apply all of these changes to that graph, to the graph you see on the screen. But I can't do them all at once, and the order I do them in actually can affect the answer. And you might be thinking, how is that possible? So if I shift it down first, right, down 2, so it looks like this, right? So I'm taking this graph, shifting it down 2, and then I flip this over the x-axis. And if I do that literally, now a lot of students don't literally flip it over the x-axis. They kind of flip it over in place. And if that's what you do, you actually still end up with the right answer. But if you're doing this literally and saying, now I want to flip it over the x-axis, what's going to happen to this graph is it's going to flip, like this point here, that's at -2. When it flips over, it'll be at +2, right? And so it's going to look like this, right? So that's what it would look like if you flip it over, if you shift it down first and then flip it over. Whereas if you flip it over first, like this, and then shift it down 2, you get this graph. Right? So it's the same 2 changes, but applied in reverse order, and you can see that it makes a difference with what the graph looks like. So that's why you have to be careful on how you apply those changes. So we want to do this one first. We'll do this second, and we'll do the stretching or shrinking last. Right? That's the order you want to apply these changes in. So this is actually on the right track. Right? So we're taking the basic function, we're flipping it over first. That's what I've done here. And then maybe I should just erase this one. Let's do this. Okay, erase that. I can. And then put a big red X through this because that was not the right path to go. So first we reflect it, which means it's going to look like this. Second step is not only shift it down 2, but we can also shift it to the left 2 at the same time. So remember, these can be applied simultaneously if you're using my method for applying these transformations. Right? And so we're going to do our tracking point, right? We have this point at 0, 0. That's going to get shifted to the left 2 and then down 2. And so it's going to end up at -2 on the x-axis and -2 on the y-axis. Otherwise, it just gets copied and pasted. And so this gets copied and pasted to this location now, so it's going to look something like this. And then we do stretching or shrinking. Now, we haven't talked about how to manage stretching or shrinking yet, but it actually, if you're using the technique that I'm suggesting, doesn't add any additional work to the problem. The way you account for stretching or shrinking is to plot points. But notice, we've been doing that on every problem anyways, right? So when I got to the bottom of this problem, what did I do? I plotted some points. I didn't have any stretching or shrinking. I just graphed these points to make this graph as accurate as possible. So if there is stretching or shrinking, you're just going to plot some points, which is something you would be doing anyways, in order to account for the stretching or shrinking, but also to make the graph as accurate as possible. So the stretching or shrinking, if you're using my technique, doesn't really bother you because you're going to be doing this either way, right? And so we're going to set up a chart. We already have an idea of the pattern of the graph, the shape of the graph. We have an idea of where it's located. And so we're just going to plug some numbers in. So again, I'm going to plug in -1. So we have a square root, so we want to try to be mindful of choosing numbers that work out nice with that square root. and -1 is a number that does. All right, and so I'm copying this equation down here, and I'm plugging -1 in for x, and then I'm going to simplify, right? So -1 plus 2 is 1. The square root of 1 is 1. -2 times 1 is -2, and then -2 minus 2 is going to be -4. Let me try that again. Now, if there were no stretching, if that 2 wasn't there, then this would have been a -1 here. It would have been -1 times 1, which would have been -1. And then I would get -3. So now you can see the effect that the stretching has. So instead of being at -3 for that point, it got stretched out and is now at -4 instead. So I'm going to redraw my graph for my final answer. So we have -2 here, -1. And we'll have -1, -2, -3. We're at -4 now. I don't know if I'm spacing those appropriately. Hopefully it doesn't mess up the way the graph looks, but we have -2, -2, and then -1, -4, right? It would have been here, but now it's going to be at -4. So you can see again, it's being stretched vertically. And so what's going to happen is instead of this being a sharp curve like it is here, by stretching it vertically, it's going to be a more rounded curve. It's going to be more gradual. I don't know if I'm using the right words to describe that, but you'll see what I mean here once we get another point drawn. So let's do one more. Now, what's another good choice for x so that it works out nice with the square root? 2 would be your next best choice. So I'm going to plug in 2 here. I'm going to be lazy instead of rewriting everything. 2 plus 2 is going to give me 4. The square root of 4 gives me 2. -2 times 2 is going to be -4. -4 minus 2 gives me -6. So again, it would have been, if that 2 wasn't here, I would have had -2, I wouldn't have had -2. I would have had -1 times 2, which would have been -2. And I would have got -4 here as an answer. But instead, because of that 2, the stretching is causing me to get -6. So we have 2, let me mark it over here. We have 1, 2, that's what we're choosing for x. And then this needs to go down a little bit further to -6. And so now we're going to be here. Whereas we would have been here, just to kind of, well, no, not even there. I don't know if I'm drawing this very well. We would have been here instead. So you see the curve would have been like up here, but now with the stretching, it's getting pulled vertically. And I really feel like I need to redraw this. So let me try it one more time. Oops, I'm doing the wrong button. Okay. That 6 is just a little too far down. Again, you want to, of course, these are kind of spread out far too, but we should put these closer together. I think that'll give us a better, drawing. So 2, 6, whereas it would have been here. All right, and so now I'll connect these points. Okay, pretty bad, but okay, get the idea. I don't know, I feel like I should try one more time. I'm just afraid it's going to be worse than what I did. Yeah, okay, it already started off worse. Okay. Oh, geez, okay, here's what I'm going to do. I've had to do this before. I'm going to pause my recording, and so you don't have to sit there and watch me make all these horrible attempts at graphing, and then I'll resume it once I'm happy with what I've drawn. So yeah, so that always happens. I paused it, took my time with it, drew it more slowly, and I was happy with it the first time, but while I'm live on camera, I guess I'm just in a hurry, and I can't seem to get it right. So this is a good image of the graph. And again, you can kind of see what it would have been like if we didn't have the stretching. So kind of see the effect that has. Domain and range, because it just asks for that on every problem. So the domain, I'm not going to write it on the screen, but how far to the left, how far to the right. The furthest to the left it goes is -2, and then it goes forever to the right. And then the range, how far down does it go? -infinity. How far up does it go? -2. And so that would be the range, that'd be the domain, and we're done with that one. So why don't you guys try this problem? So pause the video, consider the equation that you're given, and decide which of the graphs seem to match that equation based on the transformations that need to be applied. And then resume the video to see if you came up with the right answer. And also find the domain and range. Okay, so the correct answer in this case was answer B. So the reflections you should have identified, not the reflections, the transformations you should have identified were reflection, right? That was one of them, flipping the graph over, shifting to the right 5, right? The -5 shifts it to the right 5. And then there was a stretching factor of 6, which you really could have figured out the right answer without knowing that. And this is, again, the problem with multiple choice. You don't really have to understand the topic a lot of times to just eliminate answers until you find the right one. This is the only graph that does shifting to the right 5, flipping the graph over, which again, I'm indicating in the wrong order, but you flip it over first, and then you shift it to the right 5, and this is what you would get. And then you can see that the stretching really makes this a very narrow parabola shape. Without the stretching, it would have been more broad like this, but stretching it vertically makes it a more sharp parabola curve. And this is the only one, but without the stretching or shrinking, you would know this is the right answer. It's the only one that's shifted to the right and flipped over. The domain, all real numbers, goes forever to the left, forever to the right. So -infinity to infinity. The range, how far down, -infinity. How far up? Well, this point's the furthest point up, and it was shifted to the right 5, but you don't want to use 5 in your range because 5 is the x coordinate for that point, right? It got shifted to the right 5, so we're talking about x equaling 5. You want the y coordinate, right? You want the largest possible y value. That's what the range is asking for. And so this is the highest point on the graph. The y coordinate for that point is 0. So that's the largest y coordinate that this graph can produce. And so it goes from -infinity to 0. All right, one more topic and then we're done. And it's a completely unrelated topic for the most part. And it's kind of like doing the increasing, decreasing, and constant in 2.2. I didn't really talk about it in that video, but there are certain topics that they need to fit somewhere in the textbook because it's a topic that has to be addressed for a lot of college algebra courses, but there's not really a good place to fit it. It's not enough to make it its own section. So it gets shoehorned into these sections where it doesn't really connect to the material, but it just needs to be placed somewhere. And so that's what happened with increasing, decreasing, and constant. And that's what's happening with even and odd functions. So an even function is any function f of x with the property that f of -x equals f of x. All right. An odd function is any function f of x with the property that f of -x equals negative f of x. So we're making really clever use of the function notation to describe this particular property of these special functions. The first thing I want to say before I dig into what that special property is that not all functions have to either be even or odd. In fact, most functions are neither. And so that's always a possible answer on these questions. So it'll ask you, is this function even, odd, or neither? If you were to just randomly pick a function, odds are that it would be neither. Even and odd functions are really special functions that don't usually occur by chance. They're, maybe that's a bad way to put it, but if you take all possible functions, most of them will be neither. Even and odd functions are really special properties that only apply to some functions. And so just probability-wise, if you're picking a function at random, it's likely to be neither. But that being said, on the homework, these are going to be chosen very carefully where even and odd will be answers very often. But, if we go back to the problems we looked at previously that aren't about this topic, those functions are all neither for the most part. I think all of them are, right? This one's not even or odd. This one's not even or odd. I'm pretty sure all of these were neither. But these are going to be chosen a little more carefully where you will get some that are either even or odd. Now, what's special about an even function? Well, what's happening here is, remember, f of anything is a y coordinate. It's a y value, right? So this is producing a y value when I plug in -x to the function. This is producing a y value when I plug in positive x to a function. And we're saying that those two y values are equal to each other. So what's happening with an even function is you're plugging in the same number, right? X, it means they're both being called x, which means x is representing the same number in both cases, but in one case it's positive, in the other case it's negative, and you're getting the same answer for y for either case. So what's special about an even function is you get the same y value for positive x as for negative x. In other words, doesn't matter whether I plug in positive 2 or negative 2, I get the same answer either way. Doesn't matter if I plug in positive 5 or negative 5, I get the same answer either way. That's how an even function behaves, not just for one particular number, but for all numbers. So whether I plug in 7 or negative 7, I get the same answer. Whether I plug in 8 or negative 8, I get the same answer. That's what makes a function an even function. You get the same answer. It doesn't care whether the number is positive or negative. You're going to get the same answer either way. Now, as you change the numbers, the answers are going to change. A good example of an even function would be y equals, well, let me use function notation since that's what we're doing here. F of x equals x squared. It's a really simple one, but the square function, the basic square function, is an even function. Right? So whether I'm plugging in positive 2, right, which is going to give me 2 squared, which gives me 4, or negative 2, which gives me negative 2 squared, which also gives me 4, I'm getting the same answer either way, right? So whether I plug in positive 2 or negative 2, the answer is going to be 4 regardless. Whether I plug in 3 or negative 3, the answer is going to be 9 regardless. So I'm getting the same answer whether I plug in 3 or negative 3. I'm going to get 9. I'll get the same answer whether I plug in 4 or negative 4. We get 16, right? So what I can say, because I'm getting, because f of 2 equals 4 and f of negative 2 equals 4, what I can say is that f of 2 is equaling f of negative 2. Or let me to follow this order here, let me put it the other way around. And let me write it a little bit better. F of negative 2 equals f of 2, which just equals 4. I could say f of negative 3 equals f of positive 3, which is going to equal 9 for this function. Right? That's what makes a function even. It's a really special property. Right? So can you figure out can you decode this? What is this saying about the function? What's its special property when it's odd? Right? So maybe take a moment, maybe pause the video, think about what is this telling you about odd functions? What's its special property? So the special property for odd functions is that, again, you get y from this, you're getting y from this, but this one's negative, right? So, and that's what's equal. And so what this is saying is that you'll get, how do I want to word this? Whether you plug in the positive or negative of a number for an odd function, you'll get the same answer, but opposite sign. So how do I normally say this in class? When I plug in the same number but with the opposite sign, I will get the same answer but with the opposite sign as well. So for even function, you get the same answer regardless, positive or negative, you get the same exact answer. But for odd functions, you get the same answer but with opposite sign. So if you plug in numbers with opposite sign, you get the same answer but with opposite sign as well for odd functions. So a good example of an odd function would be f of x, you maybe have guessed this, equals x to the third power. Funny how even powers, even function, odd power, odd function, right? There's a little bit to that. It's a little more complex than that, but there is something to that. So if I plug in 2 here, I get 2 to the third power, which is going to be 8. If I plug in negative 2, I get negative 2 to the third power, which equals negative 8. And so I get the same answer, but opposite sign, when I plug in the same number, but opposite sign. That's what an odd function does. That's the behavior of an odd function. And so again, I can write this as f of negative 2 equals negative of f of 2, right? Because f of negative 2 is negative 8. F of positive 2 is positive 8, right? So f of negative 2 just equals the negative of f of 2. I know it maybe sounds confusing when I say it really fast all together like that, but it fits that description, right? Okay, so the problems you're going to have to deal with on the homework are, here's a function, is it even, odd, or neither? And I used to teach this, maybe up till a few years ago, using these definitions. I would say, well, here's how you tell. And I still really prefer this method, but it is challenging. It's difficult for students to apply the concept. But the way you would tell, the more theoretical way of determining this is to consider what happens with f of negative x, because that's the litmus test here, right? What does the function do when you plug in the negative of a number versus when you plug in the positive of that number? So what you want to do is look at f of negative x and see what does it do with that negative sign. If it ignores it and just gives you the answer f of x, then it's an even function. If it takes the negative sign and just processes it and puts it outside the function, then it's an odd function. And if it does anything else, it's neither, right? But like I said, that can be complicated. Maybe I'll show you one example of how to use that method. But what I've transitioned to is just to do experiments. Try plugging in positive 2 and negative 2 and seeing what the answers look like. If you get the same answer both times, maybe it's an even function. Now, remember, the reason I'm saying maybe is because it has to work every time. So you shouldn't just draw that conclusion from one experiment. You need to check it a couple of times. So if it works for 2 and negative 2, check it for 3 and negative 3 also. And if it works for that one, then you're probably safe to say it's an even function, because it'd be a really weird coincidence for it to work for those two but nothing else, right? And so, but at least check it a couple times. If you plug in 2 and negative 2 and you get the same answer but opposite sign, that's an indication that it's an odd function. But maybe check it one more time just to make sure. Try 3 and negative 3, for example. And just check by experimentation. Plug in numbers to see if it behaves like an even or an odd function. All right, so let's try that with this particular, let's try it both ways, right? So here's the old way that I would teach it. We have f of x equals 5x to the 8th power minus 5x to the 6th power. So the way I would have taught this previously is the way you check to see whether this is even or odd is to see what happens when you plug in negative x in place of x. Right? So I'm replacing the x with a negative x because I want to see what it does with that negative sign. Does it just make it disappear? Does it ignore it? Does it like somehow neutralize that negative sign? Because if it does, it's probably an even function. If it's able to somehow make that negative sign go outside the function, like it just kind of takes it and throws it out to the beginning of the function and makes the whole function negative, then it's a non-function, right? But if it doesn't, if it's a mixed result, then it's neither, right? So what does this function do with this negative sign? So I'm going to replace these x's with negative x's. Right, so I'll get 5. In place of this x, we'll get negative x to the 8th power. I need to use parentheses because of the negative sign. Minus this x gets replaced with negative x, and then that gets raised to the 6th power. Well, what happens when even powers are applied to negative signs? They become positive. The negative sign does just go away here, right? So negative x to the 8th power is just going to be x to the 8th power, because that power being even really just kind of negates or cancels out that negative sign. Maybe I shouldn't say negate, because negate and negative are too similar of terms. Same thing's going to happen here, right? This is an even power, so when you take a negative number to an even power, it comes out positive every time. And so you get back to your original function, right? I'm saying the wrong thing here. 5x to the 8th power minus 5x to the 6th power, that's just the original function. So I can take this is the right-hand side of the original function. I can replace it with the left-hand side, which is just f of x. This thing here is your original function f of x. So what you've just proven is that f of negative x, when you simplify it, just equals the original function again. It just goes right back to equaling f of x, which makes it an even function. Right. That's the more proper way of proving that this is an even function, with theory, with definitions. But because this method we're about to use, doing experiments, doesn't really prove it, because like I said, this has to be true for every possible value of x. And this proves it. This proves that no matter what x you choose, you always get back to your original function, because we never picked a number for x. We proved it in general for any x that this relationship is true. That's why this is a more formal, rigorous, strong proof that this is an even function. Excuse me, I'm starting to get my words scrambled. I can't even say that. It's a long video, so I'm getting a little bit tired of talking, I think. So Whereas when you're doing experiments, you're really only proving it's true for those values that you're checking. And you're just taking the chance, if you will. And it's a good chance. The odds are good, but just because you check it for a couple of numbers doesn't mean it works for every possible number. But you can feel pretty confident that it will, right? If it works for a couple numbers, it's very unlikely that it was just coincidence. And the chances are that it's going to work for every number in the same way. So here's how you do it by experimentation. Pick a number for x. Don't pick 0. It won't work for 0. But pick 1. 1's a good choice, right? So we'll try it for 1, and we'll plug it into the function. So we're going to plug 1 in for x. We get 5 times 1 to the 8th power. I'm going to need more room here. Let's do that. Minus 5 times 1 to the 6th power. Oh, this isn't going to work actually, because this is going to equal 0, right? Do you see that happening? This will be 5 minus 5, which equals 0. Why does that not work? Because to tell whether it's even or odd, we have to see whether the answer comes out the same or the negative of the previous answer. But with 0, we won't be able to see if it's the same or if it's the negative, because 0 doesn't, carry a sign. So I can't choose 1 actually, because this is going to equal 0 and that just messes it up. So I didn't want to do 2 because the number is going to be big. That's why I was trying to avoid that, but we don't have a choice here. So let's choose 2 for x. And we'll plug in 2. Right, so we'll get 5 times 2 to the 8th power minus 5 times 2 to the 6th power. Now I'm going to have to grab my phone, not to show you how to flip it over, but to use it as a calculator. And I'm going to have to turn it sideways to do that kind of an exponent. Okay, so we have 2 to the power of 8, which is 256, times 5. All right, so I'm going to get 1,280 from that, minus we'll have 2 to the 6th power, which is 64, times 5, which is going to be 320. So now I'll subtract those, and I will get 960. If I did that right. Okay. So we get 960 from f of 2. So what do I need to do to see if this is an even function? What's the next thing I need to look at? Well, if I'm checking f of 2, I need to compare that to f of negative 2. So I need to choose negative 2 for x this time in order to check to see if it's behaving like an even function. I want to see what does it do when I make the 2 a negative and I look for f of negative 2. All right, so I'm going to get 5 times negative 2 to the 8th power minus 5 times negative 2 to the 6th power, and I want to see what result I get from that. And what's going to happen is this will still equal 1280, because when you take negative 2 to the 8th power, it's still going to come out positive 256 times 5, so I still get 1280. This negative 2 to the 6th power will still be positive 64, times 5 is going to give me 320, and so I'm going to get 960 again. Right. And so I meant to ask this before we got to the result, but how will I know if it's an even function if I get the same answer when I plug in negative 2 as I did when I plugged in positive 2? So if these work out to be the same, that's an indication that it's an even function. Now again, it doesn't really prove it. It just, we're kind of going with the odds here, that if it works for one number, 2 and negative 2, it'll work that way for all the other numbers as well. But you probably should check at least one more time. I'm not going to on the video, but maybe check 3 and negative 3 just to make sure you get the same answer again. And from that point, you can be pretty confident that it's an even function. All right. How would I have known if it was an odd function? What answer would I have gotten here to prove it was an odd function? I would have gotten negative 960. I would get the same answer I got before, but with a negative sign, the opposite sign. And that would show me that it's an odd function. And if I got anything different, if I would have got like 5,000 here, 960 and 5,000, it's neither, right? It doesn't fit either description. All right. So let's take a look at, I have maybe a couple, or maybe more than I thought. Okay, a few more examples, and then we can be done with this video. I'm sorry about how long it's taking. I thought maybe it would take like an hour and 15 minutes, and I'm already at an hour and a half, so I apologize for that. All right, what about this one? All right, so let's just check these by experiment. I won't do both ways this time. Let's just check by experiment. This time we can choose 1, it's not going to zero out. I can tell by looking at the numbers here. So we'll plug in 1 for x. So we get f of 1 equals 2 times 1 to the 4th power minus 1 to the 3rd power. That's going to be 2 minus 1, which equals 1. So when I plug in 1 for x, I get 1 for y. So what do I want to compare that to? What do I want to plug in for x next? If I'm choosing 1 to test, then I have to plug in -1 to complete that test. And how will I know if it's even? When I plug in -1, what will I have to get here as my answer for it to be even? I would have to get 1 again. I'd have to get the same answer I got before. That would show me that it's even. How will I know if it's odd? The answer I get here will be -1. I get the same answer I got over here, but opposite sign. So I would need to get -1 over here. If I get anything other than those two cases, then it's neither. All right, so I'm going to plug in -1 for x. Now be careful, this gets really tricky right here. Plugging in -1 for x, because we have a minus sign in the equation, plugging in a negative for x, -1. So be careful about those negative signs. So we're going to get -1 to the 4th power, which is +1. And let me make some more room here. And so we'll get 2 times 1 here, which is going to be 2. Here, -1 to the 3rd power, we have to do the exponent first. Remember, order of operation, you do the exponent first. -1 to the 3rd power is going to be -1. And then we take the negative of that. We want to subtract -1, which is going to make that +1, and I get 3. So what's my conclusion? It's neither. This one's neither even nor odd, because for it to be even, I should have gotten 1 here again. That's how I would know it was even. For it to be odd, I should have gotten -1 here. The same answer, but with the opposite sign. I didn't get either of those things, and so it's neither even nor odd. All right. Let's check. Oh. Okay, let's see. Now, what you'll learn is that for polynomials, if all the powers are, I'm trying to think of the quickest way to end this video. If all the powers are even, then it's an even function. If it's a polynomial like this, if all the powers are even, it'll be an even function. If all the powers are odd, it will be an odd function. So that's a shortcut a lot of students will use. If it's mixed, like this one, right? We have 1 even power, 1 odd power. It's neither. Now, with that shortcut, you do have to be careful about constant terms. So if you have like x to the 5th power plus 2x to the 3rd power plus 7, now this looks like it might be odd because odd power, but this constant term counts as x to the 0 power, which is an even power. And so this actually would be neither again because it's mixed. You have odd and even powers. So be careful about those constant terms. They count as even powers of x for that shortcut. All right. So if it's all even powers for a polynomial, it's an even function. If it's all odd powers, it's an odd function. If it's mixed, it's neither. But that only applies to polynomials. That doesn't apply to radicals. It doesn't apply to absolute value. In those cases, you have to do your experiments. All right, so why don't you check these to see if they're even or odd? Let's start with this one. And I really don't like using y there. That's confusing. Let's just switch it back to x. You're more than welcome to do that. That letter you use for the variable can be changed. So let's just call it x instead. All right, and so we're going to have f of x equals the 9th root of x. Is that an even function, odd function, or neither? Pause the video and come up with your result. And then check, and then resume it to check and see if you got it right. Okay, so here's one way you might have gone about doing the problem. Probably the easiest way is to choose 1, because with 9th root, if you pick a different number like 2, or even if you pick 9, the 9th root of 9 does not simplify very nicely. It would be a pretty big number. You have to pick a pretty big number to get the 9th root to simplify past 1. And so I maybe should have gave you that hint. For your experiment, 1 would have been a good choice for the number you should choose. All right, so you plug in +1 to see what the function does with that. 9th root of 1 is just going to be 1. And then you plug in -1 to check to see if it's even or odd, right? You have to take the same number you chose before, but opposite sign to see what it does with that negative sign. Now, because it's an odd root, it doesn't come out imaginary. For odd roots, the negative sign just passes right through. So the ninth root of 1 would be 1, and the negative sign just passes right through. So the answer you get here is -1. So you're getting the same number, but opposite sign. That's an indication that this function is an odd function. And so we would choose odd in this case. All right. One last problem in this video is over. All right. So same thing. I want you to do this one as well. So, oh, it's not quite over actually. I forgot to talk about symmetry. Oh my gosh. Okay. I have one more thing I have to tell you guys about before we can finish this video. Oh man, I almost feel like I want to cry. I'm ready to be done, just like you guys are. Okay. I completely forgot to mention this. I apologize. All right. So let's check to see if this is even or odd. All right. So pause the video, do your experiment, see if it's even or odd. 1 is not a good choice here because if you plug in 1, you get 0. And 0 is not a good way to tell if it's even or odd. You have to avoid 0. So try 2, for example, and then check to see if this is even or odd using that. Okay, so what you should have concluded for this function is that it is an even function because you get the same answer from x equals 2 as you do for x equals -2. In both cases, you get the answer of 3. And if you were to check it with other numbers, you would find the same to be true, that whether you plug in the positive or the negative of a given number, you get the same answer from the function either way. And that makes it an even function. Now, the thing I forgot to talk about was what that means about the graphs of these functions. So if a function is even or odd, the graph of those functions will have a special kind of symmetry. And one of those symmetries I've already talked about earlier in the video, which is symmetric to the y-axis. So even functions, and this is kind of a mess right here. I'm trying to think, where could I put this? I guess I really just maybe forgot to even include it in my lesson, I feel like. But it's obviously in the question here for us to talk about. So let me add a blank page, I suppose, and then we'll write it out here. So even functions are symmetric to the y-axis. And I kind of mentioned what that means earlier. And so a good example of this would be the V shape that we talked about. So the absolute value of x. So here's the y-axis right here. I'm doing a bad job. Here's the y-axis. And this graph is symmetric to the y-axis, meaning for every point on one side of the y-axis, there is a mirror image point the same distance away. So whatever that distance is right here, let me try drawing that again. So whatever that distance is, let's try it this way. Whatever that distance is, you go that same distance on the other side of the y-axis, you'll find a mirror image point located there, right? I'm not really happy with that either. There we go. Okay. So right there. So it's the same distance away on the exact opposite side of the y-axis, you'll find a mirror image point. So for every point over here, there's a mirror image point same distance away on the exact opposite side of the y-axis. That's what symmetric to the y-axis looks like. And when there is symmetry to the y-axis, it's a really nice property to be aware of because when you're plotting points, you basically get a 2 for 1, right? So for every point you do the work for on this side, you get a point for free on the other side. So you do the work for 1 point, but then you get a second point for free. So it's like buy one, get one free. For odd functions, there's asymmetry, but it's a little bit more unusual. For odd functions, those functions are symmetric to the origin, which is not a line. It's not symmetric to an axis. It's symmetric to a point. And this one I've had trouble over the years trying to describe. I think I have a pretty good description of it now. So a good example of this would be, y equals x to the third power. Right, so that graph, which we didn't really talk about as a family in this video, but I'm just going to show you what it looks like. Looks something like that, but maybe not quite. It doesn't really exhibit the symmetry I wanted it to. And so the origin, remember, is the point at 0, 0. And the way this symmetry works is for every point on one side of the origin, so let's say like right here, there is a mirror image point the same distance away on the exact opposite side of the origin. Right, so whatever that distance is, you go that same distance away on the exact opposite side of the origin, and there's a mirror image point located there. Same distance away on the exact opposite side. Now what happens is as you move around the graph, the opposite side of it is going to change. The angle kind of changes, right? So the exact opposite side of the origin for this point is going to be like down here, but same distance away, right? And so that's how symmetric to the origin works. So odd functions are symmetric to the origin. Even functions are symmetric to the y-axis. So for this problem, even though it asks about that symmetry first, probably the best way, because this graph would be kind of hard to figure out, absolute value and x squared mixed together. It's kind of a tough function, right? So maybe the best way to determine the symmetry would be to do this first. Is it even or odd? We found that it's even, and you just have to memorize. If it's an even function, it's symmetric to the y-axis. You just have to memorize that fact. If it's even, symmetric to the y-axis, so we choose that. If it's odd, it's symmetric to the origin, and if it's neither, if it's not even or odd, then there's neither symmetry. Right? So let's go back to these problems. This function is odd, so is it symmetric to the y-axis or to the origin? It's symmetric to the origin. So I don't know if it would ask you this after this question, but if it does, because I think they normally do, I just didn't capture it on my picture, my screen grab, this will be symmetric to the origin because it's an odd function. And this one, it's neither, and so it has no symmetry. So notice I actually didn't even pay attention. It was asking that here. What's the symmetry? And I just marked neither because I was thinking it's neither even nor odd, but it wasn't even asking that at that point. But we're going to say no symmetry, which is it's a little misleading to say that because maybe there's some kind of symmetry to this graph, but none that we are currently familiar with. So as far as symmetry goes, we'll just say no symmetry or neither if the function is neither even nor odd. So that concludes the video. I'm sorry, this is embarrassing how long this took, 1 hour and 45 minutes. But I think I did a pretty thorough job. Hopefully you understand the material in this section and the time was well spent. That concludes the video on section 2.3. I will see you in the next video for section 2.4.